Alright, so this is the first video I'm going to make on a series of videos talking about the isoperimetric problem and solving it using the calculus of variations. So let's start off with what the problem is. So the problem is in 2 dimensions. Say you have a curve of fixed length. So let's say that you have something that looks like this and it has a fixed length L. So you want to look at what the maximum amount of area it can enclose is. So the way to think about this is say you have a string of some length and you tie it up so that forms a little loop. And then you put that string down on a table and you want to say what's the maximum amount of area on this table that I can cover. And so you can have many shapes. You can have a blob, or you can maybe arrange it into a square shape, or you can arrange it into a bean or something. And you want to say this is A1, this is A2, this is A3. So which shape would maximize the area that you have? And it turns out, spoiler alert, that the answer is the string must form a circle. And so that means that if you have some fixed length L, then the maximum amount of area you can enclose is the area of a circle with perimeter or circumference L. And there is an analog in 3 dimensions where you say you have a closed surface that can be a cube or a box, which is I guess a cuboid, or a tetrahedron, icosahedron, or whatever. And you want to say if you have some closed surface of a fixed surface area S, what's the maximum amount of volume V that you can enclose? And again, the answer is analogously a sphere. And you might have heard that if you've taken a bio class that cells arrange themselves in spheres because that way they can enclose the maximal amount of things inside of them while having the minimum amount of surface area required. And so the problem is nice, but the way to solve it is also really nice, which is the calculus of variations. So the idea of the calculus of variations is that say you have some function or a curve and you have some properties of that function or curve, like say the area bounded between the function and the y-axis, or the length of the curve, or the volume that you get when you rotate the curve about the x-axis, or so on and so forth. And hopefully you've seen that these problems can be solved by some sort of integral involving the function. And the idea of the calculus of variations is that you take these what are called functionals, which is a function of a function, and I'll explain what that is in a bit with some examples. But you try to find a function that optimizes this value. So for example, you can say, okay, between 2 points, what's the curve that takes the least length? And you should know that that's a line. If you have 2 fixed points, then the shortest path between them is a line. And you try to find what sort of curve optimizes a certain property. And so you can use something that's very analogous to calculus, where you take something that's similar to the derivative called the first variation, which I'll talk about in the next video, and you set that equal to 0 to find an extreme value. And the extreme value might be a maximum or a minimum. To check that, you have to do some more work. But the idea is just to find an extremal, and then usually, based on the scenario, you'll only get one solution that's obvious as to whether that's a maximum or a minimum. So anyway, that was a lot of random words. So I'll try to explain what I mean a little bit. So let's say that you have your 2-dimensional coordinate axes, x and y. Should I use my other marker? And let's say that you restrict your attention between your x values a and b, and you have 2 points here. Let's say that this is a, this is your point b. And let's say that you have some curve here. And so actually I'll take off the label of y here, because I'll call this function y, which depends on x. So this is a function y of x, and that's some curve joining the 2 points a comma capital A and b comma capital B. So we can ask some questions about it. So for example, what is the area between the x-axis and the curve? And so you probably know that that is equal to the area from the integral from a to b of y dx. So this is just the area between the x-axis and the curve y of x. And I just left off the x here, it's implied. And the reason I'm using j of y, I don't know, it's just what the book uses. But the idea is that you have the endpoints a and b, which are fixed. And so you have a function here, which is your input, and then your output is a number. So for example, you can have a parabola and you can figure out what's the area underneath that. And so your input would be the quadratic parabola, whatever you have, and the output would be the area that's underneath it. And so this is like a function, which is j, of functions, which is your input y. And so in this case, you might ask, for all curves joining the points A and B, what is the curve that minimizes the area between the x-axis and the curve? And so let's call this j1 of y. We can also ask some other properties of a function. For example, we can ask what is the length of a function. So that can be like j2 of y is equal to the integral from a to b of ds. And so ds will be like some infinitesimal arc length. So what that means is, like, say we zoom into this portion of the curve. So our curve looks something like this. So our ds will be this length here. But then by the Pythagorean theorem, you can sort of make this into dx and dy. You can say that ds is equal to the square root of dx squared plus dy squared. And so hopefully you've seen this before, but this is the same thing as the integral from a to b of square root of 1 plus y prime squared dx, where y prime is the derivative of your function y. And you can just sort of get that by factoring out the dx here, and it just works. So this is saying you have your input function y, and then you have this expression which gives you the arc length, and that gives you a real number, which is your output. So again, your input is your function y, which could be like a parabola or whatever, or a like circle, semicircle, whatever. And then it'll give you the arc length of the thing. Another thing you can ask is maybe j3 of y, which is just another functional. And you can ask what happens if we rotate this curve about the x-axis. What's the volume of the figure that we'll have? And hopefully you've also seen that this is equal to the integral from a to b of pi y squared dx. So if you try to use the calculus variations on this one, you'll sort of ask what is the curve of possibly minimum or maximum length that joins A and B. And so you should know that that will be a straight line, which minimizes the length. And for this one, you can ask, like, what is the curve so that when you rotate about the x-axis, it'll cause the minimum or maximum amount of volume. And you can find that out by solving that. And so another example that you can have is, say, j4 of y is equal to the integral from a to b of x ds over the integral from a to b ds. Or if you want to write that out more explicitly, that would be like x root 1 plus y prime squared dx over integral from a to b root 1 plus y prime squared dx. So this, as we saw here, represents the length of your function. And this whole expression represents the x-coordinate of your center of mass of the function. So what that means is, like, say your function is represented by some sort of string which has like unit density or like uniform density throughout the entire string. Then what would be the center of mass, or the x-coordinate of the center of mass? That would be given by this expression. So notice that this expression is kind of more complicated than these ones, because here you have an integral of something, but then here you have the ratio of two integrals. And so optimizing this thing, like optimizing the center of mass, would be kind of more difficult to do. And so what are we going to do? We're just going to like ignore things that look like this. So the main functionals that we'll be looking at will look like the following. So we're going to take some function f of three variables x, y, and z, and we're going to consider j of y, which is the integral from a to b, and you know what a and b are, of f of x, y, and y prime. And then usually you'll have some conditions on y. So for example, here you're fixing the endpoints. So you want to consider not all functions, but maybe like all functions that join these two endpoints. So for example, these are possible functions that you can have, but something that looks like this would not be valid because it does not pass through the second endpoint. So you want to say out of these first three, or any curve that touches these two endpoints, what is the optimal value of this functional? And so you can impose conditions like y evaluated at a is equal to capital A, and y evaluated at b is equal to capital B. So starting off, you'll look at functionals that look like this, and later on we'll get to more complicated stuff, like you can do parametric functions, you can do things in higher dimensions. So for example, some of these f's up here, f would just be y, For this one, f would be square root of 1 plus z squared, because if you substitute y prime for z, then you get square root of 1 plus y prime squared. And here, for example, f would be equal to pi y squared, because it's just the second variable. And so I also included an x here. For example, this expression, even though we're not going to consider the ratio to integrals, the top integral involves an x, and so in some problems you use an x. And to be the most general, I'll include the x as well. And so the idea about this is that you can find something that's analogous to the derivative, again called the first variation, which I'll explain in the next video. And you can use that to optimize these things, and you can actually even do more complicated problems. Like you can say, let's say you fix some length. So that means that you're fixing a value of the functional. So you're saying j2 of y is equal to L. And now you're not only imposing these two conditions, but you're also saying these conditions plus j2 of y is equal to L. And you may say, okay, for all functions that satisfy these three conditions, what has the optimal area? And that, to solve that, it's actually analogous to like Lagrange multipliers, which you might have seen if you're taking multivariable calculus. And yeah, using parametric functions and this multivariable, this Lagrange multipliers idea, we'll be able to solve the isoperimetric problem in 2 dimensions, and then we'll go up to 3 dimensions as well. So to understand most of the content that I'll have in the next couple of videos, you should have at least some familiarity with multivariable calculus and some differential equations. Or if you want, you can just take what I say for granted if you haven't seen that stuff before. But anyways, yeah, so that's this video. And then in the next video, I'll start to explain some more of how you can do calculus with these functionals.